So let's continue. Please welcome Armin Ronacher, Flask and Ginger second creator. Welcome.
Hello everybody. So this is a little bit of a sort of continuation to Linux talk, because it has to do with security and there's some little bits and pieces of it itself. If I'm too fast, just give me hand signs and I will try to slow down. So my name is Armin Ronacher, and for the most part I'm doing Python open source libraries, but my day job is to work in a Tokenbased company as a sort of online infrastructure engineer, whatever you want to call it. And we build almost exclusively APIs for computer games. So when you play one of our computer games, you will sign into our services and we will store all your stuff there. And this talk is sort of a second version of a talk I gave earlier about how to build secure things and how SSL works, but it has more of an emphasis on actually the security concepts behind it and not so much about SSL. And this is almost all motivated by 2.5 years of trying to deal with security systems for computer games. And I think this is basically the motivation. Who here has used SAML? Or had to use SAML? Nobody. That is shocking. SAML is literally the worst thing ever created. It's an XML-based security concept, and it's certified by how many authorities, and it's a piece of garbage, but it's secure. But if you try to use it, it looks like nearly impossible to actually build a secure system with it, because it has so many moving parts, and nobody understands all of them. So instead of teaching you how SAML works, I will show you how to build secure systems yourself, and then you can figure out if you actually want to use SAML or build it yourself. So first the question is, why do we want to have secure APIs? Why is this even necessary? And I'm not going to tell you that the NSA is going to steal all your data. Instead, I'm going to tell you that Starbucks is your biggest enemy. Because Starbucks killed the, it's just unencrypted. Starbucks killed the unencrypted connection. Because every time you go into Starbucks and you log into their Wi-Fi, you might lose your data because someone else is sitting on the same Wi-Fi and has a little program running sniffing all your data. And the reason for that is that Wi-Fi is an unidirectional system, so every node in the Wi-Fi network sees everybody's traffic. And because our network security itself is disgusting, you might as well send all the data through someone else's computer without really noticing. Because your enemy serves on the same Wi-Fi as you, and if it's not your enemy serving on the same Wi-Fi as you, then maybe there's a little person sitting somewhere on a corporate network and trying to sniff some data out. So, what do we have to secure in order to protect ourselves against people on Wi-Fi? The most important things are pieces of information that allow an attacker to become you. And that's usually session cookies, it's access tokens, and then things like credit card numbers, because really you don't want to share them. So don't be afraid of the government for this talk, be afraid of the person sitting on the same Wi-Fi. So I think there are two types of APIs. So first of all of this is web technology, there is no other stuff. So everything is HTTP or HTTP-like protocols. And I think there are two types of web APIs. One are web APIs, and the other one are browser web APIs. And the difference between those two is who is your client. So if you are a Python server, and you have a Python client connecting to your Python server, then you might speak HTTP, but there is never a browser involved. So a whole bunch of security garbage that a browser does, you don't even have to be concerned about. And the other thing is browser web APIs, where there's a browser, and there's a JavaScript client sitting in the browser connecting to your web service. And those are two very, very different things. And the reason for this has to do with who to trust. If you are a browser, or if you build an application that connects to a browser, then if you want to have an encrypted connection between your application and the browser, you need to trust somehow that the connection between the browser and the server actually goes to the server you think it does. And this is provided by public certificate authorities. So when when a user connects to this bank, there's a little lock icon in the URL, and it says, you're now connected to this bank. And it's secure, verified by Komodo. And that's useful for user, because they see this little lock icon, it's nice, and they don't need to do anything else. But it's hugely misleading, because what this actually means is that there's one person in Komodo that at one point gave you a phone call to verify that you actually own this domain, and did a basic background check that you are the person that you claim to be as the server provider. And when you are a backend service and you have a client that you wrote as well, why do you have to use a certificate authority? Why do you not directly verify that this is your server, because you can prove that this is your server? So you can throw this whole certificate authority garbage out of the way. And this is basically the biggest differentiation. So if you are using a browser, so you're building a regular web application, then a lot of this what's in this talk doesn't apply to you. Because really certificate authorities are, for the most part, the only thing you can really deal with. But for everything else, and this is a lot, you can use much better like security principles, and I will show you some of this. And even if you think like, oh, all I'm doing is building a web application, that's not true. That's not true, because very often a web application connects to another web application. For instance, if you are doing credit card processing, you're connecting to a payment gateway. If you are signing in with Facebook Connect, you're opening an HTTP connection to Facebook as well to verify access tokens and a whole bunch of other stuff. So for any service-to-service communication, there are much cooler concepts than certificate authorities. So my point is, if there is no browser involved, you do not need a certificate authority, at least not a public one. If there's a browser, nothing you can do. So in order to see what a certificate authority does, I want to look at something else first, and that's the concept of what trust is. And trust is basically the most important thing about the security system in my mind. And the biggest two terms there are authenticity and secrecy. And there are probably other terms for this, but this is what I use. And they're two very different things, but they're related to each other. Authenticity is when there's an author of the message, and the receiver can trust that the author of the message is indeed the person he claims it is. So if Alice sends a message to Bob, then Bob knows that this was the message from Alice, and if it went to someone else in between, he would know this. So there's a very strong indicator that the message was not written by someone else. And the second, but that doesn't mean that the message is secret. Like that message could be public, and everybody who gets hold of this message can read it. But the second part is secrecy. And secrecy means that if the message goes between the author and the receiver of the message, everybody who had the message in the meantime could not read the message. And you cannot have secrecy without authenticity. And the reason for that is that a message, if you cannot verify that the author of the message is the author of the message, someone else could have decrypted the message in between and re-encrypted it and told you this is actually the message, but he has read it. So that would be an active man-in-the-middle attack. So if you have authenticity of completely unencrypted messages, then Alice can send a message to Bob, and Eve can read it, so she's wiretapping. But she cannot modify the message, because Bob would notice if Alice is no longer Alice, but has become Eve. But if you have secrecy without authenticity, then Bob is completely clueless about anything. He got an encrypted message, so he has this feeling that everything was secure. But what actually happened is that Eve got the message in between, decrypted it, and re-encrypted it. So this is where certificate authorities come useful. Certificate authorities mean that unless Eve paid a lot of money to a certificate authority and convinced them that she's actually Alice, there is no way for this message to be still authentic. But that certificate authority system is very huge. There are like 160 companies involved, and each of those companies have many employees, and you only need one shitty employee in one of those companies, and there's a good chance that they issue a wrong certificate. And this has happened before. There are a whole bunch of really big CAs that issued fraudulent certificates for Google and other companies. And Google certificates, if they're fraudulent, they're easy to spot because Google is big. But if someone issues a certificate for your service, there's a good chance that you will not notice. What's even worse is that some people run, like we do computer games. One of the things you notice with computer games is you run this on a Windows machine usually, and on Windows machines there's this thing called antivirus software. And antivirus software cannot read downloads properly that are encrypted. So what they do is they man-in-the-middle you on your own computer to decrypt your message, to check if there's a virus in it and re-encrypt it. So they put a little fake certificate root on your own computer. They man-in-the-middle your connection in name of security. So sometimes you don't even notice that this is happening. So how do you verify authenticity? And the most useful concept for this is signatures. And a signature adds something to a message. That's authentication, which means that you can be sure that the message was written by whoever has access to the secret key. It adds integrity, which means you can verify that the message has not been altered on transit. And then it adds a little thing which is completely useless for APIs. It's called non-repudiation, I believe, and it's basically the idea that the author of the message cannot claim that he did not send the message. This is, for the most part, something you don't really need if you write APIs, and if you remove that part, you end up with message authentication codes. It's basically a little token that verifies that the message was written by a person that has the secret key and that has not been altered in transit. That's all it does. And when you have message authentication codes, then in 6 steps you can send one message from person A to person B and verify that nobody has seen it in between. So the first thing you need is a secret shared key. So the consumer and the producer, let's say the author and the receiver of the message, both of them have the same key. That could be a big random string. And you then use a cryptographic signature concept to sign this message. And the most common one is HMAC, which is hash-based message authentication. So the first person sends the message, takes the secret key and the message, and it signs it. And then it sends this message on to the server. And the server has the same key, the same secret key, and then verifies that the signature is correct. If the verification is correct, it handles the request, creates a response, signs it again, sends it back to the client. So the key, the secret key, has never been sent over the wire, which means that Eve, if she would get the message, could read it, but she cannot modify it because she doesn't have the secret key. So key is never on the wire, and Eve is a very sad attacker. So, but she can read the message. So what's the worst that Eve can do? Eve can do a lot in this case. So we are not talking about encrypted connection here. It's just a verified connection. So what Eve can do at this point is she can intercept the request and never ever send it. This is something that Alice would notice because none of her requests go anywhere. The second thing that Eve can do is she can send the request and not tell Alice. So Eve continues talking to B but doesn't send any responses back. This is also something Alice would notice. Eve can get a little bit more tricky and can send the request many times. And one time she tells Alice, but then 5 times she executes it more without telling Alice. The usefulness of this with an HTTP protocol is not particularly huge, but it's still something you should be aware of. Eve could just wait. Eve could take that signed message and wait for an hour and then send it. And it's almost the same as not telling Alice. Eve could send it delayed and not tell Alice. In this case, we have Eve sending it to Bob, but telling Alice, and we could just send it once now and then a second time a day later. Or if we have something like a parallel universe Bob, we could send it to that guy instead and not to the original Bob, which is very unlikely, but that's something she could do. And for a lot of things, none of these problems actually matter. And the reason for this is that all of the things on these slides that I've shown you so far are pretty much exactly the same thing that happens if I pull the cable. basically I partition your network. And I don't know, you probably have not seen this because a lot of the things you're doing is between server and browser or between server and server, and they either have very reliable network connections or people don't notice. But for instance, we do mobile games. And one of the things that people do with the mobile games, they're on a little iPhone, and they go into the London Underground. In the London Underground, there is no 3G reception. And one thing that happens surprisingly common is that the client sends a tiny request, like for instance, I want to buy this game item. And then the message goes to the server starts the purchase request, but in exact this moment, the user goes into the tunnel. The server fully purchased the item, but the user never saw that he purchased it because the return channel was broken because it was in a tunnel. So that's a very common example of something that's shitty for the user and that you need to deal with. Because the user, the worst thing that can happen for the user is he comes out at the other side of the tunnel and says, oh, there was an error, let's buy it again. And he purchased it twice. So to solve this problem, there's a concept called idempotency, which means that you can execute it as many times as you want, but it only ever does it once. How many of you have implemented idempotent things on their servers? Not enough. So here's how you do it. You put a nonce in the cache. So a nonce is a number that's generated once, and the client, so normally you have an API called purchase. And you call this API call and it purchases something. With a nonce, you have a little modification. You put a random number. The client, before sending a request, generates a random number that's large enough, like a UID. And it sends this random number along with the message. And ideally, it puts it into the signature. And this random number, the server looks at and verifies if he has ever seen this random number before. And if he has seen the random number before, he will not do anything and instead just reply. And this is how it would roughly look like. So you have a function called handle request, which takes a request and should return a response. And the first thing you do is you generate the expected signature for this request. And if the signature is not the same as the one that you expect, then you know someone tried to modify the message on the wire. And you just abort with an error. That means if was there. But the second case is the request has been sent a second time, like if tried to send it like 5 times. Or the client had a network communication problem and tried to retry the request. In that case, if the nonce has not been used, you perform the modification. So you purchase the item, and then you remember that you have seen this nonce, and you store the nonce in Redis or something else. Then you generate the result, and you also generate the result if the nonce has previously been used because you want to return the same response, and then you generate the response with the signature. So this is fairly straightforward. It requires a little bit of re-engineering of how the code works, but not only do you get a really nice signature-based request-response system, you also get the guarantee that a client can always retry the request. And that's awesome because it means that your application works on really shitty networks. So there's obviously one problem. If these random numbers are stored for eternity, then you're going to store a really large cache of nonces. And more important, we also have this case where what happens if Eve sends the request a day later. Like, she does the request once now, but then a day later, Alice has completely forgotten that he purchased this item. Eve just purchases it again. And then Alice just had to pay double the price for something she didn't want. For this, we have a very simple concept, which is that signatures have a timestamp in it and they expire. So not only does your signature contain the signature and the nonce, it will also contain when it was being created or when it expires. So when you have expiring signatures, you only need to store the nonce until the expiration of the signature. Because when you already know that the signature is too old, then there's no point in storing the nonce because you will never ever accept the request. And in order to have expiring signatures, you have to synchronize your clocks really well. Because I don't know if you have used cloud machines at one point and you've noticed that all of the machines have vastly different clocks. So if you're on Amazon and you just boot 6 machines and you wait for a month, you will see that the machines are more than a minute out. And that's because timekeeping computers is apparently a really hard problem. So in order to not have this problem, you need to have NTP installed on your servers. That all the servers once a day really have the clocks properly synchronized or constantly. Because otherwise you will end up in a situation where you generate a message on one of your machines and it gets verified on the other one and it's instantly invalid because the message is already in the past. But once you have your clock synchronized, this works. Now there's an obvious problem with this, and that's if you have a client that doesn't have a synchronized clock, then this whole trick doesn't work. And most common case is iPhones again, because or any Android phone or any smartphone. Because for instance, there's this game called Candy Crush Saga, and people have figured out if they send their clocks into the future, they get free candy or whatever. So you have users that live in the year 2030 because they just put their clocks forward. Now at one point, all of their cell certificates break and they can't use the internet anymore, so they must set the clock back. But you're definitely going to see phones that are more than 5 minutes out of sync. So this trick doesn't work if you need to generate the signature on their phone. But it does work really well if you generate the signatures into servers you control. So the verification looks almost the same. The biggest difference is that you split the signature of the message and then you also you basically put into your signature, into your message, you put a header in the payload, and the header contains more information. Like the header it could contain the nonce, but it can also contain when it expires. And if the expiration time is in the past, then just say signature expires, I'm sorry, go on, try again with a new signature. And everything works as it does before. So the nice thing is you store way less nonces, and also it solves the problem of replay attacks where someone just comes in a day afterwards and tries again. Now, in order to do this whole signing business, you can implement this yourself, or you can use a library called Centros, which is what a lot of people are using now. It started out as a clone of the Django signing framework, but it's now a standalone library which also supports JWS, which is JSON Web Signatures. So you can use this to talk to certain web APIs that use something like this. And it does all of the complexity of signing for you, and it has secure string compares and all of the things that are needed. And this is, for instance, used if you use the Flask framework. The session information that you have in Flask is signed this way. So you have secret key. If you send someone session information, then the session cookie is signed with its signatures. And this is how you use it. It's very simple. You just have a function which makes the serializer from a secret key. The secret key would have to be stored somewhere, so you can either have a secret key that's shared between the application and the other server, or if you have OAuth clients, for instance, many OAuth applications, each OAuth application has its own secret. So you would get a secret specific to this application. And then when you make a ticket, it looks like the JSON module. There's a dumps function, and it takes a dictionary and it stores this dictionary in a signed message, and then puts a signature on top of it. And this message looks like base64, so you can put it into URLs, in activation links, in emails, all of that stuff. And when you get it back with the verify auth ticket, it reads it again, and it also checks if the expiration is in the past, and if it's okay, it extracts the use ID out of it. So you can use this, for instance, to prove that you are the person you say you are. So if you use Facebook Connect, for instance, you go through this OAuth flow and everything, and at the end you end up with a bearer token. And if you give this bearer token to Facebook back, it will tell you, oh yeah, this token belongs to person X. And you can do something like this with signatures. So for instance, we have with a game client and a game server. And the game client signs into our system, and it shows the main menu, and you can purchase all of the things. But then sometimes there's this moment where you need to sign into the server to play with other people. And for us to prove to the server that the client is indeed the person it says it is, we generate one of these tokens. The client takes this token, brings it to the server and says, oh look, 2 seconds ago I verified with my authentication provider that this is me and this is the proof for it, and then a server takes the proof and goes back to the authentication provider and says, can you verify for me that the client is not lying about themselves? So that's a very useful concept to send things around in a secure way. Because you don't need SSL for this. And in fact, there's a good chance that if you put SSL for this, you might actually not solve the problem. Now, there's one problem with this. Certain things will still require SSL. So I'm not saying don't use SSL. In fact, almost all of those things work much better on top of SSL. But even in the absence of SSL, you already have a pretty good system. Now, how many of you used OAuth 1 and it's like the Twitter OAuth, something like this. How many have used this? How many of you enjoyed signing requests with it? Probably nobody, because it turns out that signing killed OAuth 1. So that was the big argument against OAuth 1. It's like, oh, I have to sign this request and it's complicated. And people just did not want to sign. And I think there are a bunch of reasons. First of all, the signature protocol that Twitter had was ridiculously complicated and it didn't work for some things like PHP 4. But this is solvable. But it has one problem. If every request you do to your server needs to be signed, then you can no longer use the curl command line executable. Because each request you're doing will have a different signature. And you want to just go into your command line and say, I want to HTTP get this response. And I want to see it in my terminal. And with signed tokens, that's no longer possible. So one solution we have for this problem ourselves is we have a command line executable that wraps curl and does the signing automatically, so you can still play with it in the command line, but it does add friction. So as an alternative to signing everything, there is token-based authentication. And token-based authentication is the core of OAuth 2. So instead of signing every single request and not sending the secret key around, you get a token, and that token verifies that you are this person for an extended period of time. And this only works if you have SSL. Like, there is no way around that. If you do not have SSL, then token-based authentication just does not work. But it does use short-lived tokens, and it sort of lowers the chance of what happens if you lose your token. But with a signed request response cycle, the worst an attacker can do is it can send the same request another time or not at all, but it cannot modify a request. It cannot, for instance, say, oh, you want to buy one candy thing, I'm going to make you buy 100 of them. You cannot do that. But with a token-based authentication, the token is the same for every request you're doing. So if Eve would be able to intercept this communication, she could buy you 100 of these candies instead of one, and your credit card bill all of a sudden looks much bigger. And so we need to have SSL for this. But OAuth 2 at least tries to mitigate the disaster that token-based authentication can do by splitting tokens into two pieces. There's an access token and a refresh token. And the access token is sometimes called a bearer token. And this access token lives for a short amount of time. So basically, if someone steals this token from you, he has only about 12 hours, or how long it's configured to last, to use this token. If he wants to use it the day afterwards, it's invalid. And he has no chance with this token alone to make the token last longer. So that's basically all security is, just make disaster as small as possible. Because if this token expires after 12 hours or after 24 hours, you need the refresh token to refresh it. And the refresh token is on the wire much less often. And this token is usually the refresh token usually lives for eternity, or at least for a really long time. And it's usually a piece of signed blob. So the problem is Eve can do pretty much anything with this. So use SSL, otherwise it doesn't work. And it's really just a trade-off. So you have about 24 hours of damage asset, and if someone steals this token, you have a problem, but only for that day. And the most common case for these tokens to get stolen, for us at least, is accidental leakage. So we have computer games, and with computer games they tend to crash sometimes, at least during development and with the QA department. And then the QA department sends a log file back. And that log file contains the access token because it showed somewhere up in the traceback. That's accidental leakage. If someone takes this token and the token didn't expire by the time we got the log file, we can sign in as that QA department guy. And this is just the QA department in this case, but you also sometimes have this case where if you use Android apps, there's a thing on the application, on the system called logcat. And logcat is like a syslog. So there's a huge log file which is writable for every part of the system. And there was a case where Dropbox had a debug log where it debug logged its access tokens into logcat. And any application can read logcat messages. So if you had Dropbox installed on your Android phone and you also had a malicious app installed on the Android phone, that malicious app could read the log files and try to find the token and then use the token to do something funny with your account. So it's very easy to accidentally lose these tokens. So be careful with them. So if you do want to use access and bearer and refresh tokens, the way to do that is to store the access tokens in Redis for a short amount of time, like for instance for 24 hours, and have the refresh tokens not stored. And the reason for that is that one thing you will notice is that if you write APIs for other people, that people are lazy. They're very, very lazy. So when it's like we are a server team and a game team. And when the server team built this authentication system, the game team said, oh, refreshing is too hard. We will not implement the refresh token, at least for a start. So if we would have to store the refresh tokens, every single request would create a new refresh token. And because they live for like a month, a year, eternity, it would just spam our database with garbage. So I strongly recommend to actually sign the refresh tokens, because at that point you don't need to store them. The only thing you need to store is the secret key, which signs this thing. And per user, you would have what's called a generation number. And the generation number basically means that when I think I lost my refresh token, then I want to have a revoke button. And pressing this revoke button removes access from everything I've ever granted access to. And it does it by incrementing this number. So every time I refresh the refresh token, I check if the generation number is not newer than what it should be. Because, not older than what it should be. Because that would mean that the user wanted to refresh this token. So if you ever go to your Twitter app panel, there's like a button, revoke all device access. It basically would increment like a generation number or something of that sort. And then all you have to do is sign off this refresh token. It says, this is valid for this user, this is my generation ID, and I put my access token into Redis. And then every time a request comes in, I look into Redis if there's a token in there. If there's a token there, I use it. If the token is expired, I tell the user, hey, your token expired. Please come back with the refresh token. And if he sends me the refresh token, I go through the decentralization step. Check the signature of the refresh token, and so forth. So the question is, why would I not always use the refresh token? The answer is simple, because it's so likely that we accidentally lose these tokens, and nobody ever presses the revoke button, and because the refresh token only, in a perfect application, only ever goes over the wire once every 24 hours, the chance that someone accidentally, like the chance that you refresh this token, for instance, because you're at Starbucks and someone intercepts your SSL connection, is much, much lower. So it's just a trade-off. So this brings me back to SSL. Everybody's using SSL, and everybody I know is using SSL through public certificate authorities. And I want to show you that you can actually use SSL, at least for a lot of things, without having to go through public certificates. And the reason for this is, the reason for a lot of what comes in this SSL part is that certificate verifications do not work. And this is a huge problem. Now, if you remember Heartbleed, when Heartbleed happened, first of all, it was hugely embarrassing that it happened. But people figured out pretty quickly, I mean, within a week, that it's actually surprisingly easy to get private keys out of this thing. Now, if you have a publicly signed certificate, you pay money to a company to sign you the certificate, and they sign it for 2 years. And that's how they make money. So you lose the certificate, but now your private key is leaked, and the certificate is valid until 2020. what can you do? Nothing. There's absolutely nothing you can do. You're fucked. And that's just really disappointing. And the reason for this is that how would you ever figure out that the certificate was revoked? Just imagine this. You have your browser, like there comes a request in and it says, oh, I'm from Microsoft.com, and look, my certificate is valid for 2020. Now your browser would have to go into the internet and verify that the certificate is not revoked. So for a start, for every domain you're visiting, for every 12 hours or so, it would have to go to a server to verify that the certificate is still valid. But what happens if the internet doesn't work because the server is down? Or even more problematic, captive portals. So you're on an airport, and the internet connection is blocked until you enter an email address, or until you press the buy button for 25 minutes. If the connection is intercepted at that point, and the browser could not go to the internet to say, is the certificate still valid or not? The browser has two choices. It can say, all right, fair enough, I can't access the revocation list, so we'll just let you pass. That's stupid, because at that point, I could just be the attacker and say, oh, revocation lists just always don't work, so just don't bother, accept all certificates. And the other option is even worse. It means that if you can't access this certificate authority to verify if the list is revoked, the key is revoked, I just don't let you go into the internet. So the end result of this is that not a single browser implements certificate revocations. So even if you pay some money to revoke a certificate, and like Cloudflare revoked, I think like 80,000 certificates in one day and made a huge spike on the internet, it's more marketing than anything else, because really certificate revocations do not work. So what can we do instead? And the answer is we do the same thing as we do for token-based authentication. You treat it as if private keys can get lost. So how do you minimize the risk of a lost private key? Now the first thing is, this does not work with publicly signed certificate authorities, public certificate authorities. But it does work with self-signed certificates. And self-signed certificates, unlike what the internet tells you, are actually really good for you. Just not for normal users. But if you are one service talking to another service, self-signed certificates are awesome. Because you can become your own private certificate authority. And what you do is you make certificates expire every 24 hours. So if someone loses the private key, then there's only 24 hours of damage. And it's basically you do exactly the same thing as you do with refresh tokens and access tokens. The refresh token is your root CA. And the access token is the certificate and the private key you're using for this connection only. And they're obviously not the same at all. They have nothing to do with each other. But from a security point of view, you could look at it like this. The certificate travels over the wire, the private key does not. But if someone accidentally has like a heartbeat bug on his server, then the private key might leak. But after 24 hours, the private key kind of becomes useless. So how does it work? Basically, you create a root certificate, and you sign it with your own key, and you always trust the certificate. So you have this root certificate embedded into your application. And you have a cron shop that issues certificates on an isolated service with all the ports closed every 12 hours, and it sends it to all of your web servers. And this web server then uses that certificate and private key to sign the connections, and you cycle the certificates every 12 hours. It means that your private key is like completely shielded off, like the really critical one, the root CA one. So the maximum damage is really very close. And that would work. And it survives heartbeats surprisingly well. The problem is, certificate authorities will not let you do that. But first of all, this is how you would verify it. If you use Python requests, you make an HTTP request list request, and then you say verify equals the path to my certificate. And that's the certificate, the root certificate. And you can use that. But why does it not work with public certificates? And the reason for that is, first of all, the whole CA system is just not very good. But you need, if you sign a certificate with a public certificate authority, like Komodo, you go to the web panel, you sign in, you go to two-factor authentication, then you upload a certificate signing request, then you click a button on the CGI script and wait 10 seconds, and you get the sign stuff back. And they're usually valid for a year, and you need to pay every time you press that button. So it really just currently doesn't work. But if you run your own CA, you could try to experiment and see how you go forward with this. Now, I think there's an argument to be made that at the moment so I would say about 5 years ago nobody cared about SSL much, besides some internet activists. Now everybody uses SSL. Like every shitty blog has an SSL in front, and like I'm supporting internet freedom and have SSL on it. And the end result is that we have so much more SSL now than before that there is more interest in trying to make the system secure. And because it clearly doesn't scale well, people are now looking at it and trying to improve it. So there's a good chance that the public CA system will be improved and replaced by something else. There is a certificate, I don't know what it's called now, certificate pinning, where if your browser sees at one point that Google.com was signed by this CA, then it will give you a warning if next time it was signed by another CA. But all of this is work in progress. It's not at all properly working yet, and it's just being patched very, very manually. For instance, Chrome is a browser made by Google, and Google thinks that if people get intercepted on Google, that's a problem. So Chrome has a hard-coded list where Google services get extra security in there by verifying that it's always one of the certificates they think it is. So it's a lot of manual patchwork in there. And it's not just Google services, it's also like I think Twitter and Facebook, like high-profile applications have custom handling in your browser now to stay secure, which is just a little bit disappointing. But it's not just like transport level security that you have to be concerned about. The other thing is that your application intrinsically needs to be secure, because otherwise someone just comes in and finds a logic error that leads to a security check being bypassed and so forth. Sometimes there's like really sorry cases of programmer bugs. For instance, there was a Dropbox problem where you could just change anyone's password. That is just, that's a problem. Like the check for the old password I think wasn't properly implemented, so no matter what the old password was, it wasn't always letting you overwrite this password. So there's a strong argument to be made that you should structure your code so that these errors are very easy to spot. And I think the most important structural recommendation for writing secure code is to structure everything you do with a request comes in and a response goes out. And you're not calling a magic function which modifies something somewhere else, because nobody that would audit the code would notice this. So if, like, Django does it perfect. There comes a request object into your function and returns a response object. And everything that happens on the response or on the request is very easy to see. Or at least it's hidden in a Django middleware. That's interesting. Well, we're running out of battery here, but maybe it works. No. Well, in any case, there are only 2 more slides. Well, if you bring me a cable, it works, but no. So in any case, if you have a request-response cycle where you get a request object and return a response object, it's very easy to audit this code. One of the things I do with Fireteam is we're also auditing other people's online service code. And the first time you look into someone else's code, you try to figure out how does the security access work. And if it's easy to see, it's awesome. If it's not easy to see, then yeah. This one here. If it's not easy to see, it's really hard to make a proper estimation of where the security bits in your code are. And it's nice if you have this one developer who knows that the security code is hidden in this module written somewhere else 3 layers down, but that doesn't help you much. And the other thing is that in Python you have a lot of support for hiding security codes so that it doesn't look into your face everywhere. But still it's very, very clear to you where your security code is hidden. Like, Django is not perfect because the security code is very often hidden in the middleware. And if you're not sure where this middleware is, you're not sure if the security code is active. But, for instance, decorators are awesome because they say this function is protected. It requires that the user has system management access. And it's sitting right next to the function. It's impossible to miss. If there's this rule of thumb that every view function you have has to have a security decorator, it's just impossible to screw up. It's even better if the function doesn't even work if there's not a decorator on it. Like, it's just becomes absolutely impossible to write insecure code. And this is something that everybody should be doing if they have like APIs. Like, have as many decorators as necessary, even if it looks disgusting, and put all your security code right where it is. Like, you should always be able to open a file and see, oh, this is protected because this code here. And just encapsulate your security systems. For instance, if you have an idempotent system where there are nonces and everything on it, there's a little bit of extra code you need to do, but if you have a class to subclass which encapsulates all the stuff, it's impossible to screw up. Like, if you have an idempotent system, you could have an endpoint class and you say, I define the parameters that go in. There's a function that's executed every time which loads the state from the database, like it fetches the user. Then if the nonce has not been used, it updates this thing. But if you just want the response, you just return the response. And all of the security things are like encapsulated in the space endpoint, and you just need to fill in the blanks, and it works. And I would recommend doing that. And the last sort of tip or sort of, I would say, basic requirement for a security system is having a concept of security context. An object that says very clearly, this is rights I have at the moment, only ever interface with this thing. And if you have written OAuth applications, it's very, very common that you sign into an application and you say, this application can only see my email address, for instance. Or this application can only write on my public wall, but it cannot read my private messages. If you have the security checks that everywhere in the code, it gets impossible to verify. But if you have this security context object, which sits around somewhere, and it says, this is currently the account on it, and these are the roles that are allowed, then you can have a simple function has role, which says, if there's an account, and the role is in a subset, if there's no account or the role is not in a subset, then you don't have that role. And otherwise you have the role if the user has the role. Like, for instance, a normal user can never accidentally become a system administrator because the user doesn't have the role. So it's very, very easy to encapsulate all of these things in the code and just hide it. And not have manual checks everywhere, which can get old and broken or accidentally removed. And if it's hidden behind decorators in the context object that's available somewhere, it's very hard to screw up. And this is pretty much it. Feel free to ask questions, also things not necessarily related to the talk itself, but like the greater picture of security.
Thanks, Armin. I have a question about using some sort of expiration for nonces, or for signatures, I would say. What do you think about using nonces for both parties, for both clients and server? Like, and don't use an expiration when you can.
If you don't have expiration, you need to store the nonces forever.
No, I mean, well, you can generate the nonce on the server and store it for, I don't know, for 1 hour or for 24 hours. And then, for in case you have an option to expire all the kind of nonces for server and
so
make all the signatures.
If you have expiring nonces, then you already have a time problem in a way. So it makes sense to add an expiration into the signature as well. Because, I mean, it gets a little bit away with clock skew if you just expire the nonces. But if you expire the nonces and not the signature, then an attacker could come in a day afterwards when the nonces are expired and redo the request. Because the nonce is no longer stored. If you have an expiration of signature, then if the nonce are no longer stored, the signature is no longer valid. So an attacker could not do that.
Yeah, but what if you build your signature using both nonces from server and from a client? And instead of letting the client to provide their own expiration time, you kind of force it from the server side by expiration time of the nonce that only server knows.
Yeah, I see what you mean. I'm not actually sure. I think in any case, you need to store these things somewhere.
Yeah, for sure, but you can like limit the time for storage.
Well, if you want, you can show me afterwards and I'll have a look at this because it's very easy to miss things in it, but I think it could work. But I'm not sure right now.
Hello. What do you think about it? That signed request with a little bit of date make server side stateless or partially stateless? That you no need to access user stored in database every time you are checking it has right, because list of rights received from client to server is signed.
So if you have signatures for everything, you can make your server almost entirely stateless. Because, for instance, you can hide as much information in the signature, in the signed token as you need. So the first time the user comes to your system, it gets this signed blob, and then it sends these around. The problem is that if that ever leaks, then it should expire at least at some point. But for instance, Flask sessions are entirely sent through the cookie all the time. So there is no reason for you to need to hit the database to figure out if the user is authenticated. So that basically goes this way. How far you want to go with stateless systems, I'm not sure. I think there are two very strong arguments. The one side says signatures are also used for everything and never hit the database. The other ones say signatures are cool, but they still kind of break sometimes, so at least every 24 hours go to the database. And there are advantages and disadvantages of those things. For token-based authentication, you don't need to store the access token in Redis. We're doing this, but the biggest reason for that on our side is actually that it allows us to figure out how many tokens we issued. That gives us some sort of fraud feedback. If everything always lives on the client, like you're sending these tokens around, you're never quite sure what the state of the system is. So having a little bit stored is useful.
And even if you store some data on a local gateway, one of grid or one of cluster entry, its data access is cheap, and the user may be linked with specified gateway by a hash or something similar, and you may not use to extensive data loading from main database, or not to do it every time.
Yeah, it's a viable concept, and lots of things work that way.
Thanks.
Thank you for your speech. But what about server-generated events? Something like you're sending via socket, some actions which performed on server that doesn't relate on the user state. What about double sending or something like this? Do you solve this problem project?
So I didn't get the last part. Which problem? You gave an example. I didn't catch the word.
Sorry.
Can you just repeat the second part of the question?
When a server generates a packet, not a user initiating a request, but a server sending some actual information to a user. How do you solve some nonce, or what about it?
So if you have, it's the same concept really. If you have one thing talking to another thing, there doesn't need to be a user necessarily. So the first thing there is that if we have two servers sitting in the same network, we have network security. So basically the absence of security is basically the answer. There's a firewall around the whole thing, and the servers talk freely to each other, which is not perfect, but it solves a whole bunch of issues like, a certificate expired, all of a sudden the service no longer works. But the normal answer to these things is if you have one service talking to another service, you can use client certificates, or at least just put SSL around it.
But, what about things that doesn't relate it to two servers? Just server sending something to user without user request at the first.
So the answer to this is we reverse the problem by making the user do something first. So for our games, for instance, there are notification channels. So you get updates from the server to the client. But it's the user that initiates it. So we have one request where you get your authentication token and everything, and then you have this token. And then when you want to subscribe to updates, you send the token back and say, oh, please subscribe me, and this is me. And then the socket stays open. And when the socket dies, you need to go through this authentication step again. So that's basically the answer. It's like it's still user initiated, but the server pushes information to the socket.
Thank you.
In your opinion, is the responsibility on security issue is more on application side or its infrastructure?
So the highest chance of someone tapping into your application is, I think, public Wi-Fi. Because it's just so simple. There are ready-made applications you download and you sniff people's stuff. So as such, there is more responsibility in practical terms on the application side, which is also disappointing because this is the part where it breaks the easiest. For server-to-server communication, you can just not solve the problem and use VPNs and just ensure that the network is secure. If you have one server talking to, like if you have an application that talks to the server and you need to provide the security on the server side, it's actually not, like there's not that much that needs to be done. Like it's the same work as for the client, a little bit less. So I think there's always more things you need to be concerned when it faces a user at one point. Because at the very least you need to inform the user in your iMessages that something is wrong. And the server is all very predictable.
Last question.
So if you control both client and server, you can use your own certificate of authority, and that's okay. But if you're using a browser as a client, how do you make this secure?
If you use a browser as a client, you have nothing you can do other than going to Google size and getting special treatment in the browser at the moment.
At the moment, and you started talking with there some movement there.
So what's happening at the moment is that, so the first thing that people noticed the first thing that was noticed as an attack to SSL that's ridiculously simple to execute is to downgrade to non-SSL endpoints. So you had a proxy that just said, oh, I'm sorry, I don't speak SSL, so let's go to HTTP instead. And in order to solve this problem, they started introducing a system, I think called HTST or something. It's a HTTP header that says, if you have ever seen me on SSL, never ever go to non-SSL anymore. And as far as I'm aware, they want to use the same system to say, if you have ever seen me with this certificate authority, then for the next N hours, don't accept a certificate that comes from somewhere else. So you basically pin the certificates into short-term cache. So for the next 24 hours, you kind of have to use this thing, which would help tremendously because it means that once you sign up with one CA, let's say Komodo, and you get a certificate from them, and then afterwards someone else comes by and says, oh, I'm actually signed by VeriSign now, you would say, oh, this is, like the browser would say, like, this is not okay. You just told me this cannot happen, yet it happened. I'm not going to let you pass. The problem with this is obviously that if you actually want to switch your CA from one provider to another at one point, until this cache expires, like there's something wrong. The thing is, this is just ultimately a trade-off, and I'm not sure whatever the solution will look like. The most interesting proposal I've seen for replacing the CA system is I think it was called convergence. It was basically the concept of network perspectives. So when instead of me connecting to Microsoft and say, this certificate is provided by Komodo and I trust Komodo, so therefore the connection is secure, what it will actually do is, instead of me connecting to Microsoft, I say, I connect to Microsoft and I download the certificate, and then I ask a fixed number of notary servers to also look at Microsoft. And if there's a consensus on the certificates we see, if I see a different certificate than a notary see, then someone sits between me and the server. So given enough notaries, I should always be able to verify that there is someone sitting between me and the server, but not between the notaries and the server. I'm not actually sure why they didn't get more traction, because the concept sounds awesome, especially because the way the protocol was proposed was that the notary requests are like an onion. So it's similar to how Tor works. A notary has like pre-batched 5 other notaries on the request. So the first notary, which sees my IP address, can never see what it verifies because it sends to the next notary and next notary and next notary. And only the last notary verifies the certificate, which means that it never sees my IP address. So it can't see that I was the person that went to like some sort of domain name that might reveal what I'm trying to do. So that is an awesome concept. That, I think, I didn't see anything obviously wrong with it, but the project doesn't seem to be alive anymore. But maybe now in light of Heartbleed and everything, and especially the NSA stuff, maybe people will pick it up again. It would be a much more interesting way to solve authority problems.
Okay. One last note. I want to note that Armin visited all Russian PyCons. Thank you, Armin, for your talk.